Hello, nice to see you.
Good afternoon.
Hi, there was some other people are joining. Hello, everyone.
Good afternoon.
Good afternoon. Last time we discussed the formation of images in case of such optical system as flat and spherical mirrors. And today, so obviously it was formation of light by reflection, because mirrors reflect light. And today our topic will be building optical images by refraction of light. So means we will deal with two transparent mediums with different diffractive index, refractive index, and there will be incident and refractive beam, which we will consider in order to build the image. And we also need to find some equation which will give us the relationship between the distances of object to the interface of these two mediums and distance from this interface to the image as a parameter of refractive indexes of these materials and curvature of this interface between two mediums. So let us switch to our slides. And for the beginning, we need to consider some model system. Let me share my screen. Okay, so that's what I was talking about. Here, for instance, we have one medium in the left side, then we have another medium with refractive index N2, and N2 is larger than N1. And we observe some refraction of incident light, which after refraction, kind of this refracted rays, they appear to converge out of this point I, which is the image of the object, this point object O. So there is distance similar to the case with mirrors. There is certain distance between object O to the interface between two mediums. So that is distance P. And also there's distance from the interface to the image of the object, which we mark as Q. So now we need to look a bit closer to this refraction process which is going on at this interface, in order to get some quantitative relationship between all these parameters. So also, yeah, important parameter is the radius of this curvature of the interface between two transparent mediums with different refractive index. So let us assume such a system, which is shown on the bottom part of this slide. We have our main optical axis, principal optical axis. Then there is some ray which goes from point object O, hits the interface between two mediums, and some portion of this light is refracted, so it goes inside the medium number 2. So there is some angle theta 1, like some incident angle. This dashed line shows us the normal to the surface at this point of incident. And also we have refracted angle theta 2. So from our previous discussions, we have shown that there is a relationship between refractive index of first and second medium, and also the incident and refractive angles. So this relationship looks like follows. So it n1 times sinus theta 1 equal to n2 sinus theta 2. So if we have very small angle theta 1, automatically theta 2 will be also small angle. In this case, we can consider some approximation, because if theta is small, then sinus theta with certain accuracy can be replaced by just theta. So in that case, we will have n1 times theta 1 equal to n2 times theta 2. Okay, so now we have this simplified version, assuming that incident angle is very small. Let me come back again to our figure. So let us now do the following. Let us express this angle theta one and theta 2 in terms of angles alpha, beta, and gamma, which are formed between the principal optical axis and incident ray, refracted ray, and this normal, which goes to the point of surface of where the incident ray hits this interface. So how do we express them in terms of like theta 1, theta 2, in terms of alpha, beta, and gamma? So we need to remember that the magnitude of adjacent exterior angle, or triangular, is equal to the sum of two interior angles. Following this relationship, we can write such equations. So for theta 1, we can write that this is equal to alpha plus beta. And for beta, it is equal to theta 2 plus gamma. So now we can express theta 1 is already expressed, and we can express theta 2 and substitute their equations, like their expressions, into previous equation. So then we will get rid of theta 1 and theta 2, and we'll stay with angles alpha, gamma, and beta. So that will result in the following equation. N1 times alpha plus N2 times gamma equal to n2 minus n1 times beta. So now we have the same like initial law for refraction written in just a different form. First, assuming that incident angle θ1 is very small, and second, we express θ1 and θ2 with just a bit different angles. Why we do that? Because it is easier now for us to express these angles with some distances of our interest, means distance from object to the interface, from interface to the image, and also the radius of the curvature. So what we can write, also taking look at this image which I have shown on the slide, that tangent alpha, again, we assume small θ1 means all angles are small. So that's why with some level of approximation, we can substitute tangent alpha with just alpha, and that should be equal to d one second, alpha d divided by p. So what is d? Let me show you again this image. So now we try to find tangent alpha, which in first approximation for small alpha will be equal, can be replaced just by alpha. So tangent of this angle alpha will be the ratio between this distance d from the principal axis to the point where the interface is hit by incident ray, by this divided by this distance between object and the surface, like interface between two transparent mediums with different refractive index. So we can proceed similar steps for other angles. That will be tangent beta approximately equal just to angle beta. That should be equal to d divided by r. And also we have tangent gamma approximately equal just to gamma, and that is equal to d divided by q. So now, taking into account these expressions and our equation for refraction under this specific condition, we can get the following equation, which gives the relationship between refractive index n1 and 2, distance between object to the interface p, between interface to image q, and radius of the of this interface between two conductive mediums. So that will be N1 divided by P plus N2 divided by Q, and that is equal to N2 minus N1 divided by R. So this is the equation which describes position of the image with respect to interface of two mediums in terms of parameters of the mediums, like optical properties, refractive index, because we don't care about extinction coefficient, which means parameter which describes absorption. We assume that our medium are transparent, so they don't absorb light, but they possess different refractive indexes. And also initial position of the object with respect to this interface between two medium. So we can consider now some specific case. For instance, image formed by a flat surface, flat interface between two medium. So in that case, if it's flat, our radius of this curvature should be approaching to infinity. So R should approach to infinity. So means that the right side of this equation, like this part, will approach to 0. So we can write N1 divided by P is equal to minus N2 divided by Q. From here, we show that Q, which is distance of the image with respect to the interface, will be equal to minus N2 divided by N1 times P. So what does it mean? First of all, I would like to draw your attention when we are talking about this equation of forming an optical image via refraction, that you need to pay special attention to the signs of this distance values, like quantities which are included in this equation. For instance, we need to focus on P and Q. So P will be positive if it's located in the left side from the interface, and Q is positive if it's located from the right side of the interface. So if we have some imaginary image, means that rays do not pass through the point of image, and it just appears that they converge from the point of image, means that's definition of imaginary image which we considered last time. Then image will be located from the same side as the object, and if object is located from left side, so P is positive, then image will be located from the same side, left from the interface, and Q will be negative. So this equation here, which tells the relationship between distance of the image as a function of distance of the object and refractive indexes of two mediums n2 divided by n1, it has this minus here, means that for flat interface between two transparent medium, we will always get image of the object on the same side as the object position itself. So if P here is positive, means that object is located on the left side from the interface, then Q will be negative, means that it's also located from the left side. If P is negative, then minus and minus will give us plus. So negative P means that object is located from the right side of the interface, and that's so-called imaginary object. So this particular case is happening when we have magnifying glass. Then Q will be positive, so it will be also from the right side of the interface. And as a result, we can claim from this equation for flat interface, object and image, they are always located at one side from the interface between this media with different refractive indexes. So let me share my screen again to make it more illustrative, our discussion. So that is the flat interface with radius of the curvature approaching to infinity. This is our object. So these are rays which are coming out from the object, hit the interface, they are refracted. And in this case, refracted rays do not pass through the image point, but it appears, if we extrapolate this refracted rays, and they converge from this image point, which is located at the same side, left side, with respect to this interface as the object. So that is the condition for forming an image by refraction when we have flat interface. The position, actual position of the image, it can vary. It will depend on the ratio between N2 and N1. So it can be closer to the interface as shown here. It can also be further from the interface, I mean further than the object from the interface, if this ratio between N2 and N1 will be more favorable for that condition. So that actual position distance Q will be determined by the ratio of refractive indexes, but since in that equation we have minus in front, that will be always in the same side as the object. And also here, that's some table which provides more information, which distances in which cases should be considered positive or negative. So you can later pay attention to that, but partially I describe it for object location and image location, P and Q. So now with this, we can make one step forward and consider so-called image formation by thin lenses. Let us look at the next slide. So lens, what represents, what actually is lens? So it's a combination of two curved or one curved, another flat. So there could be different combinations, but let's say two curved surfaces with different radiuses or the same radiuses. So we have first interface between two transparent mediums, like one with refractive index 1, let's say that is air, because usually we deal with lenses in air. So we have some glass in this shape, which forms two surfaces, curved surfaces placed in air. Refractive index of air is unity, then refractive index of glass is n. We have one interface with radius r1, which is the interface where first refraction happens. And we also have this second surface interface between glass and air with radius r2, where second refraction happens. So we can deal with first surface, find its image, and also we can deal with the second surface and find image for the second surface. So that equation which we derived previously for this interface between two transparent mediums with different refractive indexes is applicable for both of these curvatures, for forming an image of by each of these curvatures. So for instance, you can see on this example, we have two rays. One goes perpendicular to the first surface, and second one goes parallel to the principal axis, which goes through the center of this lens. So first one just goes straight, it not refracted because incident angle is equal to 0. Another is refracted. So when we extrapolate interception towards the interception, this refracted rays, which are already in the second medium in the glass, we extrapolate and get the point which is the image formed by the first curvature. So we can, in similar way, also determine image which is formed by second curvature. So let us write equations for first and second curvatures, and then our step will be to take into account that image of the first surface works as the object for the second surface in order to get the equation for whole lens as total, as one optical system. So let me stop sharing this. And we assume that N1 is equal to unity, that's air, and N2 is equal to N. That is true for surface 1. So based on our previously derived equation, considering these values for refractive index, we can write 1 divided by P1, position of object with respect to first surface, plus N divided by Q1 is equal to N minus 1 divided by R1. So that is the equation for first surface. So for the second surface, we can write that N1, now it's a medium of the lens because we go from glass to air for second surface. So that N1 will be equal to N, refractive index of glass, and N2 will be equal now to unity because second medium will be air. Taking this into account, we can write that N divided by P2 plus 1 divided by Q2 equal to 1 minus N divided by R2. Okay, so we have two equations for two surfaces. Now we need just symmetrically consider that the image formed by first surface serves as an object for the second surface. For that purpose, P2 can be expressed as minus Q1 plus T. So we consider, let me show this image again, make it more clear. So now, let's take a look here. So this is the image of the object formed by first curvature. So now we want to consider that this image serves as an object for second curvature. So what will be distance of this image to the second curvature? It will be Q1, but with sign, with negative sign, because we remember that it's considered as positive in the left side from the interface for objects, but negative when it's on the left side for images. So if we determine Q1, it's located on the left side from the interface, from first interface and also from the second interface, but we determine it first with respect to first interface. So Q1 is measured to the left direction from the interface, means it will be negative. But if we now want to consider this as a new object for second surface, then this distance must be positive. So that's why we take minus Q1, negative value of Q1. So it was negative, with that minus which we added will become positive. So then it will be just Q1, magnitude of Q1 plus thickness of this lens. And that will be this P2, distance of from the image of the first curvature to the first surface to the second surface. And it will be given by this P2, by this equation which we have just written here. P2 is equal to minus Q1 plus T. Now, as I mentioned at the beginning, we discuss image formation by a thin lens. Thin means that this thickness T is a small value. So we can neglect with this thickness T with respect to distance Q1 from the first surface to the image of the object formed by first surface. And then with some level of approximation, we can write that P2 is equal to minus Q1, because we assume that this length is thin. So now, if we substitute P2 with minus Q1 here, we will get minus N divided by Q1 plus 1 divided by Q2 equal to 1 minus N divided by R2. So now let us look here. So this equation prime is equation for first surface. Equation double prime is actually equation for the second surface, assuming that the image of the first surface serves as the object for the second surface. Now, if we sum up these two equations, prime and double prime, we will end up with the equation for object formation by a thin length. So it will be 1 over P1 plus 1 over Q2 is equal to N1 minus unity times 1 over R1 minus 1 over R2. So here we have P1, which is distance from the real object to the first surface, and Q2 will be image of this object, like distance of the image of this object with respect to second surface. Since the distance T between two surfaces is small, because we consider a thin length, then we can just rewrite this equation without this notifications for first or second surfaces. We can just consider these distances with respect to the center of the thin length, because distance between its surfaces is very small. So finally, it will be this thin length equation, 1 over P plus 1 over Q is equal to N minus 1, and here 1 over R1 minus 1 over R2. So that is the equation for a thin length. Now we can take a look at this equation under one important specific case. When rays of incident rays of light are hitting, they are traveling to the thin lens parallel to its principal axis. Do you remember in which case that happens? We discussed this case in forming images by mirrors. If rays are moving parallel to the main optical axis, like principal optical axis, then it means that the object which emits this rays of light is located very far from the lens. So P in this case will approach to infinity. So if that is true, then all refracted rays should focus in at this so-called focal distance from the lens. So in this case, Q, the distance from the lens to the image, which is formed by this lens, should be equal to its focal distance of the lens. So then we can write 1 over f. So 1 over focal distance of the lens. And this equation will actually give us the focal distance of the lens. 1 minus n minus unity times 1 over r1 minus 1 over r2. So this is so-called lens maker's equation, because with this simple equation, you need to know only refractive index of the material from which you make the lens and radius of first and second curvatures of this lens. And that will give you the focal distance of this lens. So taking this into account, because this is a constant parameter, keep in mind, that's a feature of the lens. You don't change refractive index, radius without some polishing. So if you make the lens and don't touch it anymore, don't change it. So that is the property of the lens, focal distance, because refractive index of the material is constant. First radius, the curvature of the first surface and second surface, they are also constant. So they don't change. Taking that into account, we can write equation for a thin lens in the following most commonly known form. 1 over P plus 1 over Q is equal to 1 over F. So this is the equation for an image formation of a thin lens in terms of distance of the object to the lens, distance of the image to the lens, and focal distance of the lens as its parameter based on refractive index and radiuses of the curvatures of the first and second surfaces of this thin lens. So if you have any questions, you're welcome. Summarizing our discussion today, we explain the formation of images by refraction. So first we consider just one interface between transparent medium with different refractive indexes. Got equation which relates position of object, position of image, and refractive indexes of first, second, medium, and radius of the curvature of this interface. Then we made a step further. We considered a lens, a system with two surfaces with interfaces, which represent interfaces between transparent mediums with different refractive indexes. We considered this lens placed in air with a refractive index equal to unity and refractive index of the material of the lens, most cases this is glass, equal to n. Then we considered the image of the first surface as the object for the second surface, and assuming that the distance between these surfaces is very small because we consider a thin lens, we could derive the final equation for image formation by a thin lens, which relates the position of the object with respect to the lens, position of the image with respect to the lens, and focal distance of the lens, which is determined by this equation shown, like which we got right before the final equation. Okay, guys, with this, I would like to finish our discussion of image formation, and next time we will start a new topic, which is interference of light. So it will highlight some features like wave features of light. Have a good weekend and take care. See you next time.
Thank you. Interesting lecture. Goodbye.
Bye-bye.
Thank you. Goodbye.